So yeah, I will just start my talk right now without any slides. And so who knows about side channel attacks? So many people. And who of you has already picked a mechanical lock here at 33.3? So not so many. This is basically also a form of a side channel attack. So when you pick a mechanical lock or when you open a mechanical safe by listening to the clicks of the lock or by feeling where you have to push the pins down, then you use the side channel of the sound in the case of a safe box, or the side channel of your feeling in your hand to get all the pins down. And this is a very similar principle that we apply to embedded devices in our research. And I say our research because this has been work with quite so many people actually. Like, if we had slides, then I could show it to you. So we, of course, do not listen to the mechanical sound of an electronic device like a chip, although this has been in the media, I think, a couple of days ago. This story by Shamir. Has anybody read this? That also many people. The story is actually over 10 years old, but somehow magically it reappeared. I don't know how it happened. And what we use in our research is usually the power consumption or the electromagnetic emanation of a chip. So you can imagine if a transistor switches inside a processor or inside a microcontroller, inside an FPGA, or wherever, you always have some small variation of the power consumption or the EM signal also with this. And this is the rationale behind all side channel attacks, basically, that you can detect these very small changes and that you then can extract secret keys with it. In the simplest case, you just read off a secret key. So thinking of an RSA algorithm, for instance, I think everybody's familiar with that. What the basic operation is there is you do a lot of squarings and multiplications, right? And depending on whether a key bit is set when you generate a signature, for instance, you do either a multiply or a multiply and a square operation. So a multiply operation on a processor has a different power consumption than a squaring operation. So in the simplest case, when the device is unprotected, you simply see, okay, the power consumption is higher here, lower here. So I will have a multiply and a square, which means the key bit is set to 1. And otherwise, you have just a square operation and you know it was a 0. And this was actually also how these attacks were or became popular in the academic world, let's say. So actually, I had on my first slide, I had the small logo NSA free, yeah? But now I go back a bit to NSA also. They had back in the, do we need presentation slides maybe? I have a USB.
Yes. Can you definitely see USB?
Yeah. So I'll speak on from down here, yeah? Full action. So the NSA initially, Americans had this Tempest program where they tried to read for this bulky old cipher machines the key presses that were done from a distance or read your screen from a distance through a wall. And this is the first instance of a side channel attack in this case. But in academia, it became like popular starting in round about 96. So then some biology student, Paul Kocher actually, he had his oscilloscope connected to back then banking cards and could really perform this attacks and read off the secret key. And now, we're good to go. Great. So yeah, let's F1. Oh. So it was good that we had this planned problem here. Yeah? It was, of course, on purpose. And now I can skip over all the slides. They're of no importance anyway. Yeah? So these are all the people I've been working with, quite some long list during the past few years. And this is the introduction I already gave. We're right now here and keeps this map layout in place. It has some meaning for the presentation. And beautiful Bochum is here, where this HDI is based, where all the research about IT security is done in Bochum. Looks like this, as I said, very beautiful on a non-rainy day. And Bochum had some problems in the past, so Nokia was based in Bochum, and they left Bochum, they're almost bankrupt now. Went to Romania and closed it down also there, so we have lost this industry. Opel will also close down very soon, so we have to do something new in Bochum, which is IT security, and there is where this HCI comes into play, and also a small company that I founded together with Timo, which is called Caspar and Oswald, or short Chaos, yeah? As you could see in the introduction. This I already said. Here is the URL for the mini chameleon. And here you see that we actually built it and that it actually works. I tested it successfully already with the hotel lock here. So as I said, we have, or coming to side channel attacks, we have embedded systems everywhere. This is where side channel attack usually makes sense. So this PGP thing with Shamir is kind of an exception that you perform such an attack on a PC. Usually you target embedded devices. So this is my protagonist for the presentation. It's a typical pirate. Yeah, I took him for no reason because pirates are cool. And he has the typical hat, eye patch, pack leg, and the laughter. By the way, all these most graphics that look like this, I painted them in MS Paint with hand. Not all of them. But a pirate, of course, lives in a modern world. For instance, he has his TV set connected to some set-top box, or maybe this is already built in. Inside you find FPGAs, or reprogrammable logic chips. He has, of course, a treasure chest like every good pirate, but it's not locked in a mechanical way, but with an electronic lock. So he needs some electronic token that sends radio signals here to unlock the chest, and inside is some microcontroller that does all the cryptographic operations necessary. He has, of course, a computer like this beautiful MacBook there that is so working so fine. And to log in, he doesn't use this password only, but a one-time password token also like this YubiKey. And this will actually be the 3 examples for this presentation I'm going to talk about. I hope I managed to fit it into the time that has reduced a bit more now. So this is the important circle of IT security. I put this beaver that I obviously did not paint myself as the constructive side of IT security, because this is the nature's engineer, you know. And the hacker or the pirate on the other side, and there's a very important circle that the hacker analyzes real-world products, reports the flaw to the developer, and he can then improve and in a continuous cycle build more secure products for a modern world. So this I already explained a bit. Side channel attacks, they work like in a bank robbery when you have the side channel of sound, and nowadays you use side channel of EM emanation or power consumption, and of course you don't use a stethoscope, but an oscilloscope to attack a cryptographic circuit, for instance. And this is for instance such an electromagnetic probe to record the EM emanations. This again shows what I also explained. Depending on the data you process, the power consumption varies a tiny bit. This is 1 clock cycle of an 80 mega here, and depending on if all bits are set or all are set to 0, you have a different power consumption here. This is example for the RSA, where you can directly read off the key, which was the first instance of a side channel attack, actually. So usually we use another technique, because this RSA example works fine for algorithms like RSA, which involve multiplications and squarings. But for block cipher, you have very atomic operations that work on a larger state usually. And this is where differential power analysis comes into play. It is based on a statistical test to match the measured side channel signal with small key hypotheses. So it's like a brute force attack, but you look into the cipher and then are able to find, for instance, 8-bit of the AES key at a time, because you have the side channel. I explained it usually like this. So this is from PhD comics about the Higgs boson, how it was detected. So you have basically 2 options. There is no Higgs boson, or there is a Higgs boson, and there is a tiny, tiny difference between these 2 hypotheses. Yeah? And to detect this hypothesis, which in our case is no Higgs boson, it's a wrong key candidate, or yes Higgs boson is the correct key candidate, you need to record a lot of measurements to average out the noise and then try to find the small difference. Here it says you need a huge amount of data. For our case, it varies a bit between 100 measurements and millions of measurements, depending on whether you look at a modern smart card or a simple microcontroller. Yeah, so sorry about this speed with this introduction, but I want to come to practice. And for this, I want to look at 3 case studies, and the first are FPGAs. Who does not know what an FPGA is? Nobody wants to out himself, so I can skip the explanation here. We start in our home port of Bochum and go to US. These are always the conference locations where this was presented. More precisely to the FPGA 2013 conference in Monterey. And look at FPGAs. So FPGAs, as you know, are reconfigurable hardware devices, and they're used everywhere where you need high bandwidth or low latency, things like in routers, consumer products like set-top boxes, cars, and militaries. There is some video I could not find about this huge machine gun, which then has an FPGA at the side. I could not find this, unfortunately. The problem with FPGAs is they have a large configuration bit stream, and this can be usually easily copied because it's stored externally, because you cannot fit it all into the FPGA except for flash FPGAs that also exist. But here we look at these FPGAs that have external memory. So you have some, on the PCB, you have some flash memory, and the FPGA on every boot up, the complete configuration or bit stream is copied into the FPGA. So obviously the pirate who comes along here, can easily get this bit stream and put it into a second FPGA, for instance, or try to reverse engineer that. This is now a product pirate. This is our political correct term for this. He can simply copy this bit stream, and this happened, as far as I know, for instance, to Cisco in certain countries, that the market was taken over by these copy products. So the solution, of course, is to encrypt. We're cryptographers, we encrypt. So the idea is you put a cryptographic key once at manufacturing time in the FPGA, then encrypt the bit stream with this key, put it in encrypted form into the external memory, and now without the knowledge of this key, the adversary cannot produce a second FPGA that accepts this bit stream. And of course, you can also not reverse engineer it. So the security of this approach lies in the secrecy of this key, of course. The motivation for this work was now that a colleague of mine, Ami Moradi, has already analyzed a lot of products from Xilinx, which is a market leader in FPGAs, like virtually all families up to the newer 6 series, by means of the side channel attacks. And note here, all these FPGAs have very analytically still believed secure ciphers like the AES or triple DES or so. And the question was now, what about Altera, which has a share of, I believe, 30% or something in the market. So here the situation was a bit different than with Xilinx, because there was no documentation altogether available on the functioning of the device. So it was a complete black box to us. There are totally undocumented mechanisms that are used for some key derivation, which I'll explain in a bit, and for encryption also, so we had to get to that first. Fortunately, we could do that from the design software of Altera, which is called Quartus 2 with IDA Pro, which probably also all of you know here. And the nice thing is Altera left all function names and all symbols in there. So it was, was really helpful. They simply forgot it. And my favorite is this function. The main function is called do something. This is the original name. So this do something actually does this. It takes 2 keys in this case and the unencrypted bit stream, and it outputs some files that also can be programmed into the FPGA with these keys and the encrypted bit stream. So we had to get back both parts of it. One thing is, why 2 keys? So the idea behind this is they have some key derivation in there. So the 2 keys are put in the software and on the FPGA on programming into some function which actually derives the real key that is used for encryption. So the idea behind this is, if you need key 1 and key 2 to program a certain real key into the FPGA. So even if you get this real key, let's say with side channel attack or by probing or so, you have to invert this function to program the same key again into an FPGA, into another FPGA. This is to impede cloning. So we looked at this and found it's constructed like this after some weeks of reverse engineering. So the real key is derived by taking this key 2, AES, encrypting it under key 1. So this should be a function that is, of course, only works in one way. So it should be hard to get back from here to key 1 and key 2 that generate a certain real key. So is this a good option? So we looked at it for a second, and then if I ask like this, noted, no, it's obviously not, because it's the AES here. AES has an inverse function. So you can pick any key 1 and then decrypt the real key under this key 1 star that you picked. So actually there are 2 to the power of 128 pairs that map to the same real key. So again, the idea behind this was not bad, but the implementation here was surprising to us, I would say a bit. Yeah. So having done this, we looked how the encryption is performed. So how this real key then goes is used to encrypt the bit stream here. For this, it turned out they use a simple AES encounter mode. So you have some IV that is then incremented for every block you want to encrypt. AES encrypted under the real key and then XORed with the plaintext block. So there are some issues with that, but they're not really so severe. So this seems to be fine. Note the idea why we reverse engineered all that was to do our side channel attacks. Without this information, how all the encryption is done, a side channel attack cannot be mounted because you need to know what is encrypted where. So we did a bit more, got all the file formats, some coding, and turned the black box into a white box and went on with our analysis then. So this is what the setup looks like. You have a board with the FPGA here, our own programmer to be able to send encrypted bit streams or data of our choosing to the FPGA. Then you have on top of oscilloscope, and the side channel signal is here measured with this insanely thick cable and inflexible cable. It's better for the electrons. No, so it was just handy. And here is a trigger signal that is starts the measurement on the oscilloscope by when a pin is raised by this programmer. So in this plot, you see what you actually measure on the oscilloscope. There are 2 curves here. The black one is when encrypted bitstream is put into the FPGA and decrypted on the FPGA, and not decrypted on the FPGA, sorry. So the black one is when the encryption feature is totally disabled. And the red one is when the encryption or decryption on the FPGA is enabled. So you already see some difference here. There's a higher energy consumption altogether. And zooming in, you can actually figure out where the AES takes part. So there are always small periods that relate to this AES operation. And here, from this period, we actually want to extract the secret key. So since I'm here with this, it was obviously successful. And here you can see a result of this. So this is what I already explained, this approach of differential power analysis, that you test small hypotheses for the key. And here in gray, you do not really see 254 curves in this case that relate to the wrong key candidates. And these curves that peak here are the correct key candidates. So with this method, you can identify each key for each S box separately. And with this, get the complete key. And this takes altogether 30,000 measurements, or we call them traces very often, which is 3 hours of playing around with the device and a bit of offline post-processing. So, result of first case study. The full 128-bit AES key of Stratix 2 can be extracted with around about 3 hours. And this key derivation mechanism, of course, does not prevent the product pirate from cloning. Yeah, he can just do this stuff with the AES. And another important lesson here from a more general perspective, You can do software reverse engineering to do hardware attacks after that. If you have a very complex system, you can reverse engineer parts from software if available, and then use that knowledge to attack the system. So with this, we're done with the FPGA story, and now go on, because pirates do not only hack FPGAs, but also, for instance, door locks. And for this, we go up the coast a bit to Canada. Here, Canada identified with the beaver, which has nothing to do with this engineer. It's just identified like this. And we look at the locking system, which is kept anonymous in this talk for the obvious reason. So here you have a typical door, and in an electronic locking system, the user has some form of token, can be some small hardware device, some RFID card, whatever. He touches it to the lock or holds it in proximity to the lock, and then the door can be opened. And now we look at the hardware which was used in this particular system here to realize this functionality. Yeah, in this case, there was a pretty complex authentication protocol with 11 messages being exchanged, and we had no clue how to what they actually meant. So this was, again, a total black box. However, we tried to turn this into a white box, and for this, we looked at the components of the system. We opened both tokens and locks and found a PIC microcontroller here, and also a custom ASIC put there by the manufacturer. So our first intuition was, okay, all the crypto is in the ASIC, of course. Who would build an ASIC to do non-crypto stuff? Yeah, so we looked at this, opened it, and this is what other people here can tell you even more about. I think Dimitri will give a talk on very invasive attacks, and Starbuck also knows the stuff and so on. You first dissolve a chip to look at the silicon die. So we did this. You put some acid on top, let it react, and finally you have the chip after iterating this a few times. So this is the ASIC we actually then took pictures of. This is actually a 10 mega, I think 10,000 pixel wide image stitched from a lot of microscope shots. It's a very old device in a gate array technology, so it's kind of the pre-FPGA where you just put the metallization on the ASIC and all the doping areas are already given. It's old, 2 micrometers, has some mixed signal stuff for analog stuff also, and it was pretty much utilized, but already there we could have thought, okay, there's probably no crypto in 1,700 transistors, unless very bad crypto. Nevertheless, one master student reverse engineered it all, and now yeah, it was. And this is the result, and what turns out, okay, it's all some communication logic for counting some flipping bits and waking up the microcontroller every 500 milliseconds or so, yeah. Whatever, we did it and looked at the other components. This is a PIC microcontroller, and here we're fortunate that there are known attacks on these devices to extract the program code. Because these devices, what you have to know, have some configuration bits that can turn off the readout of the program code. And this was, of course, enabled, but we wanted to see what is inside the system. So we went to circumvent this, looked first at the chip, so you can find attacks for similar microcontrollers on the internet. And we found, okay, everything looks as you would expect on a PIC. You have some memories here, you have some analog stuff here, and particularly this area, which covers these fuse bits. So the fuse bits, one interesting bit is somewhere under this metal here. We checked that it's really there, and Microchip implemented it in a way that it can be circumvented by tilting the chip a bit. So what you do is you open it, you put some tape with your hand over the memories that you don't want to erase, like the flash and the EEPROM, and then you put it at an angle under a UV lamp, and after half an hour, when enough photons have bounced under these metal layers onto the floating gate, then you can suddenly disable this readout protection. So this was pretty useful because we could get out all the code from this PIC, which is, by the way, horrible to reverse engineer because it has certain segmented memories and whatever for such a small device. But we eventually did it in IDA again. and turned a black box into white box a second time. And from this resulted now several attacks that I want to briefly summarize just here due to the time that we have. So good thing is each token here had its own unique key. So if you get out this key, you can only duplicate one token. This is like a mechanical key. You can also easily copy it with wax or so. However, each lock has an installation-wide key that is then used to derive all the keys of the token based on the ID and this installation-wide key. And having this key obtained once, you can virtually emulate every token and open every door in the system. So one option was to perform this invasive attack with the UV light. This gives you the key. Or you can also do a side channel attack with an EM probe, which you barely see here on top of the microcontroller. And this takes around about 15 minutes communicating with the lock to get out this installation-wide keys and then walk into any door. And there are some more, or were some more severe attacks that are due to the protocol design. I cannot, unfortunately, explain everything maybe next year. Yeah? One system is the cryptography inside was some mix of good crypto and bad crypto. So some vendor-designed stuff. And the more severe thing were with random numbers. You all know about random number generators, yeah? And here it was that internal values were reused in the next protocol run as values that were sent out. So you, based on this, with clever mathematics, you can derive an attack that gives you the key for a transponder just by interacting with the door without being able to open it. So yeah, this was pretty surprising. Nevertheless, we had, of course, communicated with the vendor about this. And I'll talk about this at the end, short bit. They could roll out a firmware update that at least could fix this cryptanalytical attacks that allows to open every door just by walking to it, talking to it a few times, and then yeah, have an access here. The hardware attacks are, of course, difficult to replace because you have to replace all components. And they are working now on their next product generation, which shall contain some more secure hardware where we then need other guys like Dimitri or so. Yeah, so this lesson learned here, hardware reverse engineering can enable mathematical attacks and also the side channel attacks. And with this, we come to our final part. We go actually to the heart of all piracy, as the Caribbean, where this conference was. Really beautiful, Raid 2013. It looks like this. This is one picture we took, so it's a pretty nice place to present research. And we looked at this device. This is a YubiKey 2. Who is familiar with the YubiKey? And who has one? Yeah, so no worries. This is a two-factor authentication token. Yeah, you know about this. In the past, everybody just was typing in this password. Now we know there's eavesdropping on data from all over the world. You can have Trojans on your computer and so on. So you want a hardware factor in. One option are smart cards or this SMS transaction numbers to log in. You can have the infamous RSA token. Or you can have the YubiKey here. And at this device, we had a closer look from our side channel perspective. So just to explain it very, very briefly, the YubiKey acts like a USB keyboard to your computer. So you can use it without any drivers, basically. It generates and enters a one-time password every time you press a small button on top. And this is based on the AES, so again, a secure cipher, I'd say. So on the bottom of the slide, you enter your credentials, and then you press this button, and it enters this string of characters, and they chose some encoding here to make it compatible across all keyboard layouts, so you will not find any umlauts or so in this. So every time you press, it generates some stuff. Here's always some fixed ID, and this part is AES encrypted here and then encoded. And what it contains is basically, again, an ID and several counters that are incremented every time you press a button in a certain way. So all these fields are then put into an AES, encoded, as I said, and the question is, can we get back the key? Because this, of course, enables us to duplicate the YubiKey again, or just duplicate it in software, because it generates a string, so we don't need the hardware device for that. Yeah, so for this we started again looking what is inside. There is a smart card chip inside, or is there a simple microcontroller? Here's this video. This is from an HD video that you can find on YouTube on the production. So HD videos can also leak information where the circuit is just in this molded plastic packet. So we knew then where to drill the hole, put the acid, and the result is this. This looks like some microcontroller to the trained eye with some memories and so on. And we finally also found some marking on there. It says Sun Plus IT. Probably nobody knows this, but it's in like virtually every keyboard or mouse. So it's a cheap USB microcontroller, and it has this feature to do this keyboard emulation. So this was the basic base used here. We did not try to read on any program code because we do not even know what kind of processor is that, yeah? And there's no documentation on that. So here comes now the magic of side channel attacks. You can also do an attack without exact knowledge on the hardware, and without need to do that if you know the exact protocols, which were all open in case of the YubiKey, which is a nice device, by the way. Yeah? It's a good open source design. So we did both. We tried to measure the power consumption, put in with a small handcrafted adapter here, a measurement resistor into the USB power supply, and we also put an EM probe on top of the device to make a non-invasive attack, and this turned out to be the better way. To press this button automatically, we just took tin foil. Yeah, tin foil solves everything. And if you connect it to ground, it simulates your fingers that press the button. So you don't have to press thousands of times manually. And with this, we took our measurements. We found out that the EM signal gives a better signal. This is the one here on top. The power signal is somewhat low pass filtered through some voltage regulators on the chip. And here you can, as a side channel guy, you can clearly see the 10 rounds of the AES with the 10th round a little shorter. Yeah, and from that was a bit playing around what we have to attack here. And finally, we're also able to get out the full AES key from this device in actually 700 measurements with some optimization. So this is 1 hour of physical access to the device to get the AES key out here. So again, you see this gray wrong candidates, and the one with the peaks, the red one, is the correct byte. Actually, here for a few bytes of the key, just to explain it. So management summary. Again, we can extract the key with side channel attacks, and then after that, of course, you can impersonate the YubiKey. Of course, anyway, you still need the username and the password, which reduces also the risk, so you have 2 factors also to attack. Luckily, there is an improved firmware version, so all new devices since a few months ship with this improved firmware that is not attackable in this manner easily anymore. So we come already on, still fine with time, yeah? So we come already to the final part when pirates do good or responsible disclosure. So here comes the pirate, yeah, to the designer and informs them, hey, we have a problem with your device, and preferably he does this before he publishes everything. This is how we did it. By the way, another example why pirates can do good, yeah? Maybe someone is familiar with this graph. So with the previous talk, we have here the number of pirates approximate, decreasing, yeah, 35,000 in 1820, and only 17 real pirates left in 2000. And with this, increased the global temperature by almost 2 degrees. So yeah, correlation is not causation. Yeah? This is a message behind, just to show that pirates can do some good. We also did this and talked to the people always at least 6 months before we published our stuff. The dates are a bit variable due to publication times and so on. So for the locking system, it was approximately 1 year before actually it got public. And as I said, the vendor was able to deploy a fix for this most severe mathematical attacks. Altera, we talked to them 6 months before. They said, yeah, it's like this. has to be seen what happens in the future there in this FPGA field. It's an interesting field how to protect it. It's also complicated. And with Ubicore, we also talked around about 9 months before publishing it. And as I said, there is an improved firmware version 2.4 now that mitigates these issues. So coming briefly to how to mitigate such stuff like side channel attacks, I want to show my 2 final slides, and then we come to your questions. So you can have a first line of defense. That means you can put all these classical countermeasures against side channel attacks and implementation attacks or invasive attacks in general. So you can take secure smart card circuits, which are certified, and you can modify the devices on the algorithmic level. So put randomness inside, that the measurements are misaligned or that they involve other random values that stay internal. So who wants information on this? There are a lot of books and papers, and there's a chess conference, and there are half of the people just do that. Yeah? And however, what I want to strengthen here is there's also a second line of defense, which is the system level, which you can very often also use. On the one hand, you can try to detect attacks in the back end. So for a payment system, let's say you could have a shadow account. For a logging system, for a locking system, you could have a log file if the legal situation permits that and your privacy policies. And on the other hand, you can try, instead of this detection, try to minimize the impact. And this is where key diversification comes into play. This means give every device a unique key, as it should be. Never share keys between devices where possible. So, and this I want to briefly illustrate with my final slide. Let's look at the YubiKey and the locking system. So for the YubiKey, it would be very well possible to give every token a unique key. And then an attacker who wants, let's say, a breach into a corporate network cannot simply take any key and extract the key and then go into that network, but he has to repeat the attack over and over again. And talking about 1 hour physical access to such a token, which you are likely to keep an eye on, especially if it's important, yeah, it will be very complicated in reality, and this attack does not scale. On the other hand, case of the locking system, you need 15 minutes per extracting this system-wide key, which is of no importance. It could also be 1 hour or so, actually. However, this one key allows you to open all doors in one installation. So here you have an attack that scales. You have to attack one door and then get full access. So this shows the 2 sides of the coin somewhat. Yeah, and with this, the pirate ship goes back to the rainy shores of Bochum. By the way, Bochum has direct sea connection via some small harbor and some rivers, and anchors there, yeah, to new adventures. So thank you, and sorry for the technical problem at the beginning. Questions?
Yeah, if... Okay. Thank you. Here's a question about the hack on YubiKey. If you actually increase the use counter by 700 while doing the hack, is the key any use anymore, or would the system level reject the passwords after that?
So it's not like this. So the YubiKey has 2 counters actually. It has one counter every time you power up the device. This is incremented, and this is a permanent counter. And then it has a second counter that goes up to 256, and only if this counter wraps, you also increment the permanent counter. So you would have an increase maybe by 3 or so, by 2 to 3, yeah. So this is relatively unlikely to be detected.
Microphone 1?
Yeah, you.
You had a question mark with at the unique keys for the YubiKey. So, do you know if every YubiKey has a unique key, or are you unsure about this, or do you know that some of them have the same key?
No, you can set it yourself. So there is the utility where the key is write only. So you can always set a new key, but you will render the device useless if you overwrite the old key. So everybody is free to do whatever he wants with this YubiKey. So you can perfectly set up a secure system with that. So
Okay,
you
and the
can,
default keys are random or
the
doesn't-
default keys are, I don't know, but they do not any, probably they're 0, I would say. But I mean, if you set up your system and you put the key that you cannot read into the, or you put a 0 key into your database, then it's your fault.
So you said there's an updated firmware now for YubiKey. Do you know how they protect against your attack, and are you allowed to tell?
I know partially. I would rather not speak about this now.
Okay, well, thanks.
So you can perfectly contact them.
Okay.
They are very open with this, I think.
Yeah, I was just wondering, what's the reason for that 92 and one to the last slide?
For what?
And there was a 92 here in, oh, 94.
This is the slide number.
Ah,
It's everywhere.
Really? This man is live. Crazy. Oh. Okay, the last remark is just to use this as exit, and don't forget to vote this amazing talk. Thank you.
Thank you.